Good morning, everybody, and welcome along to the AMETEK Solid-State Controls Understanding UPS Semiconductor webinar. If that's not the seminar or webinar that you were expecting, I'm sorry, but maybe you'll learn some interesting stuff nevertheless. What I'm going to do is do some short introductions, and that will allow everybody to join in who hasn't joined already. And if you don't mind, if somebody can just let me know that you can hear me, that would be awesome. Just put in the chat bar that you can hear me. If not, I'll have to try something else. So, my name is Craig Williams. I'm the Senior Technical Manager for AMETEK Solid State Controls, and I work out of the Stafford, Texas office. I have 20 years in the industrial UPS industry. 15 of those years were spent in the North Sea in Scotland, and the last, actually it's now 8 years, have been in the US. Thanks very much for letting me know you can hear me. That's perfect. I've worked with all the major UPS and charger manufacturers out there for industrial UPS systems. There will be a lag of around 30 seconds between hearing my voice and me seeing a question or me seeing any replies. So there is a 30-second delay. The platform that we use is called Webinar Jam. And the good thing about Webinar Jam is if there is an issue with the webinar, if something crashes or fails, I have a panic button, and what I can do is I can press that button. And what it will do is it will kick everybody out, create a new room, and hopefully everything will go back to normal. So hopefully we don't have to use that, but it is there if needed. The webinar will be recorded, and after it is complete, it will be available to everybody who registered. One thing about the recorded webinar, it is treated exactly like a live webinar. You can't fast forward it, rewind it, or anything like that. You just have to press play and you watch it as if it is live. Okay. And the webinar should last around 1 hour. And that just depends how much I waffle on and speak. So I was going to put an electric chair beneath me and give me a short buzz every 5 minutes if I go off topic. I'm going to try to stay as focused as I can. If you have any questions, you can put them in the chat bar. I'm going to try and save the questions until the end. But if there is something really pertinent to what I'm talking about at the time, I will see if I can answer it. Okay, so today we're going to try to understand the most common semiconductors used in the industrial UPS system, understand how each semiconductor works. We will discuss the power flow and general operation of each semiconductor, and then we'll discuss, if we have time, the advantages and the disadvantages of the different semiconductor types. Okay. So we're going to refer to this circuit quite a lot during this webinar. It's a very simple circuit. On the left-hand side, we have a DC source. On the right-hand side, we have a lamp. And in this slide, we have a switch at the top. Now, you will find that during this presentation, I'm going to make a lot of I would say somewhat generalizations about semiconductors. They're all true, but I don't go into absolute depth about what a semiconductor to do. What I'm going to talk about is how they are used in AMETEK SCI UPSs. And all of our power semiconductors inside our UPSs are designed to act like a switch. That is their purpose. They are either on or they are off. Okay, so I know this is a very simple circuit diagram, especially for those engineers out there, but it is good to show you exactly what's going on. So if the switch is open, obviously no power is going to get to the lamp and the lamp is going to be off. Okay. And then if we close the switch, then power is allowed through to the lamp. Current flows through to the lamp from the DC source and returns to the negative of the DC source, and the lamp lights. Pretty simple. So the first semiconductor we're going to talk about today is the diode. Okay. Now, a diode allows current to flow from the anode to cathode only. Okay. So the anode in this picture is on the left. Let me just draw an arrow towards it. This is the anode here, and this is the cathode here. The way I like to look at it is probably simplifying things a little bit, is the anode kind of looks like an A on its side. Okay, because I know a lot of people do have issues with anodes and cathodes. And the cathode, I know cathode begins with a C, but if you turn that C into a K, you have a backwards K for the cathode. Don't know if that'll help you, but that's how I got taught at school many, many years ago. So you have the anode on the left and the cathode on the right in this diagram here. And current, the green arrow shows you current will only flow from anode to cathode. Okay. And the diode will block current from cathode to anode. Okay. So basically the principle is the anode has to be more positive than the cathode to allow current to flow. If the cathode voltage-wise is more positive than the anode, then current will not flow through the diode. Now, electronics can be sometimes a little bit complicated, so I try to break it down into mechanical equivalents. And this is the mechanical equivalent circuit for a diode. It's a check valve. Hopefully, most of you will be familiar with what a check valve does. So on the left-hand side here, this is the input to the check valve, and this is the output to the check valve, okay? And as you can see, the flap would be normally closed if there's no pressure being put on it from the input, okay? And that means if fluid tried to flow this way, it would push against the flapper would remain closed, and no fluid would flow from right to left. Hopefully that makes sense. So this is exactly the same as a diode. Fluid, i.e. current, will only flow from left to right. That means there has to be a positive pressure or voltage higher on the anode than on the cathode. Okay. So we'll go back to the exact same circuit we spoke about a few slides ago. And instead of a switch, we're going to put a diode in there. And as you can see, the anode is on this side and the cathode is on this side. Now we have a DC source on the left-hand side here. Doesn't matter what voltage it is at this point. And the DC source has positive on the top and negative on the bottom. Okay, so it's going to drive current from the top all the way around the circuit if you follow the green arrows down and return to the negative. And because the anode is going to be more positive than the cathode, the diode will allow current to flow and the lamp is going to light in this circuit. So everything's good. Now, if we then turn the diode around in the circuit and we put the cathode on the left-hand side and the anode on the right-hand side, now the cathode is more positive than the anode. And that is the blocking mechanism of the diode. It's like the flapper. The flapper is closed now. It will not allow current to flow through this diode, so the lamp here will be off. And that is the basic principle of a diode. If the anode is more positive than the cathode, it allows current to flow. If the cathode is more positive than the anode, no current will flow. So the previous slide was with a DC source. Now we're going to make things a little bit more complicated now, and we're going to have an AC source on the left-hand side. Okay, everything still remains the same. We still have a lamp here, and we still have our diode here with the anode on this side and the cathode on this side. So The top waveform, the yellow waveform, is the output from the AC source. Okay, and the green waveform on the bottom is if you put an oscilloscope across the lamp and you're measuring the voltage getting to the lamp. Okay, now with AC, one half of the sine wave is the top. This point here is more positive with respect to this point here. I've simplified it by putting a positive and a negative there. And then for the bottom half of the sine wave, it flips over, which you'll see in the next slide. So for the top portion of the sine wave only, this is going to be more positive with respect to this. That means the anode is going to be more positive than the cathode. Excuse me while I take a drink. So because the anode is more positive than the cathode, that will allow current to flow and the lamp will light. Okay, but the lamp will only be half dim because, as you can see here, it's only allowing the positive portion of the sine wave through. So there's a positive portion there, and there's a positive portion here. This negative portion here is not getting through, and you'll see that next on the next slide. So for the negative portion of the sine wave, this side of the power source now becomes more positive with respect to this side. So it's trying to drive current in the reverse direction, which makes this side, the cathode more positive than the anode. Okay, and the diode says, no, I don't allow current to conduct in that way. Once again, if it was a check valve, the flapper would be closed and no water would be allowed to flow. So the lamp will not light for that portion of the sine wave. Okay, and you say, well, what is the purpose of doing that? Well, because we have just created DC from AC. Now, a lot of people will turn around and say, well, wait a minute, this green waveform at the bottom here, that's not DC, it goes up and down. Well, DC is direct current, and direct current means the current flows in one direction and one direction only. And if you think about it, it is flowing in one direction. It is flowing in that direction there each time. The only thing that changes is the magnitude of the voltage that's driving the current. So it is actually called pulsating DC, but it is DC because the current is only flowing in one direction. So from an AC source here, we have now created DC on the output of this circuit. And that is the main purpose that we use diodes inside UPSs. Okay. And here's a picture of a diode. This is a stud-mounted diode. They're quite common. And what you will find is one side is the tail. You would have to bolt a connection onto that. And this side here is called the stud. That's usually mounted to a heatsink. Okay. These two are not, they're not connected. There is a diode in the body of this metal casing here. Okay, and as you can see, there's a symbol right here on the diode that says this terminal here is the cathode and the stud here is, sorry, my apologies, getting it wrong. This is the anode and this is the cathode on this diode. But you can see the two diodes here are very, very similar. And you can't really see it, but there is a symbol here, and this symbol is reversed. So you can get two diodes that look very, very similar, but are the complete different polarity, because on this diode, this here is the cathode, and the stud here is the anode. And if you mix diodes up that are reverse polarity and put them into a system, you can cause severe damage. You can cause a short circuit and unfortunately let that magic smoke out that we never want to let out. Okay, we don't want to do that. And there's a close-up of the symbol. All stud-mounted diodes should have the symbol on the body of the diode telling you which side is the anode and which side is the cathode. Okay. But as time moved on, we got to more modern forms of the component. And this is actually called a SemiPAC. And this package has two diodes in it. You can see from the picture here, this is terminal 1. This is the anode of one of the diodes. This is terminal 2, and it's connected to the cathode of both diodes. And this is terminal 3. This is the anode of the other diode. And as we move on through this presentation, this is actually used in bridge rectifier circuits, and it allows you to use this package very, very easily inside the system. And another thing that I want to clear up with these types of diodes is this metal base here is only for heat dissipation only. This package still will be bolted down to a heatsink to get rid of excess heat in the semiconductor itself, but it is not connected to any of these terminals. It is completely isolated. Okay, so in the previous picture, these diodes here, they are bolted to the heatsink, so the heatsink actually becomes part of the circuit. The heatsink is live. But in these packages here, these do get bolted to the heatsink, but this is isolated from the semiconductor itself, and therefore the heatsink is not live in systems that have this package of diode on it. Okay. So that's diodes. We're going to move on to silicon-controlled rectifiers, or SCRs now. Okay. In Europe, they are called thyristors as well. So the terms are interchangeable. SCR and thyristor are interchangeable. And as you can see, the symbol is very, very similar to a diode. We still have the anode on this side here. We still have the cathode on this side here. The only difference is we have an additional terminal, which is called the gate. And we'll go on to explain what that does in just a moment. So what's the mechanical equivalent of an SCR? Well, in truth, there really isn't one. So I had to kind of try and make one up to help with the mechanical understanding of the flow of an SCR. So I call it a special check valve. So we still have the input here, which is the anode, and we still have the output here, which is the cathode. And we still have the flapper here as well. But now what we've done is we've added a gate. And as you can see in this picture here, the gate is in a position where it will not allow the flapper to move. So while there is no signal to the gate, current cannot flow this way and current cannot flow this way. The flapper will not move at all. Okay? And only when we send a signal to the gate, which in theory in this drawing here would make this block here go down and allow the flapper to move, basically sending a gate drive to the SCR allows the device to become a diode or to become a normal check valve. You remove the gate and current can flow in that way, but current still will not flow in that direction. So hopefully that didn't confuse you too much, because there isn't something out there that can actually represent the mechanical operation of an SCR, well, that I found anyway. So once again, we're going to use the exact same circuit. We've got the DC source on the left-hand side, and we've got the lamp on the right-hand side. Now, we do have a little bit of an additional circuit here. We've got a wire coming off the DC source, and it's going through a push button switch, then through a resistor to the gate drive of the SCR. So this is how we send, in this circuit for simplified purposes, this is how we're going to send a signal to the SCR to turn it on. Okay. But in this drawing here, there is no gate drive applied. So basically, if we go back to the switch analogy that we had right at the start, that means the switch is open. Okay, with no gate drive, the SCR is an open switch. Nothing is going to happen. So when we have positive with respect to negative, positive on the anode with respect to the cathode, without a gate drive, it's not going to conduct. Okay, and if we flip around the DC source and make the bottom of the DC source positive with respect to negative, the current tries to drive around. But remember, without a gate drive, the SCR is an open. It will not allow current to flow without a gate drive. Okay? So you can class it as just an open circuit without a gate drive. Now then, here's the interesting thing. With an SCR, if you then push the button S1 and complete the gate drive circuit and allow a gate drive signal to go to the SCR, it will turn on and it will start to behave exactly like a diode does. As long as the anode is more positive than the cathode, it will allow current to flow and the lamp will turn on. Okay? But here's the interesting thing. And this is what gets a lot of people when it comes to SCRs. If you remove the gate drive, so as you can see, switch 1 has now been opened again. There is no current flowing into the gate drive circuit. Everybody would think that the SCR would turn off at that point, but it doesn't. There is an inherent latching mechanism inside the SCR. It's not mechanical, it's done by the semiconductor material inside the device itself. And the inherent property is, once you switch an SCR on, and once it starts passing current through it, in truth, it does have to be above its holding current, and every SCR designed has a data sheet that comes with it, and in the data sheet, it will tell you what that holding current is. Let's just say, for ease, that the holding current for this SCR is 0.5 amp. As long as there is 0.5 amp flowing through this SCR, the device will stay on forever, as long as it has a DC source. This lamp here will stay on forever, even if the gate drive is removed. So that does confuse a lot of people. You can send a signal to an SCR to turn it on, but you cannot remove the gate drive signal to turn it off. It will stay on in this way as long as there is current flowing through it. In other words, as long as there is a voltage potential positive on the anode with respect to the cathode. Okay. And as we move on, hopefully we'll explain it in a little bit more detail about how that works. So the only way to get the lamp to turn off from that previous circuit is to actually insert a switch in series with the SCR and open that switch and stop the current flowing through the SCR. Once you stop current flowing through the SCR, it then switches itself off, and then it returns to the state where it is a completely open circuit until a gate drive is sent to the gate terminal again. Okay? Hopefully that is clear. And here's a variety of SCRs that are out there. The two at the top are stud mounted. Once again, this is actually the anode and this is the cathode. And then you've got your gate drive leads here. The red one is connected to the cathode. It's actually soldered inside this heat shrink here. And the white one here is the gate drive signal. So it's a gate cathode. You send a signal gate with respect to cathode on an SCR. Okay. This one here is very similar to the SemiPAC that we had with the diodes. There are 2 SCRs in each of these packages. And these here are the power terminals, the anodes and the cathodes. And you can see here, this is where the gate cathode signals go on this system here. And this final one is a hockey puck. I see your question, Mike. I will hopefully answer that in just a little while. So this is a hockey puck SCR. One side, so let's say this surface here is the anode and this bottom surface here is the cathode. Okay, they come in all different shapes and sizes. Usually the bigger the device is, the more current it can handle. Now the next semiconductor, and the last semiconductor we're going to talk about, is the IGBT, the insulated gate bipolar transistor. Okay. There are two symbols on this slide. The first one is a very simplified one. We have it's a transistor that has a gate, a collector, and an emitter. Okay, and one of the important things to remember about an IGBT is the gate is completely electrically isolated from the collector and the emitter. You can see there's a gap here. They are not electrically collected, and that's where the term insulated comes from in the IGBT. Okay. Now, the one on the right is actually what the majority of IGBTs, power IGBTs that come from the manufacturer are. They actually have a diode connected across the collector emitter in reverse. So the normal flow for this transistor would be current flowing through this way. And now remember, with the diode, this is the cathode and this is the anode. So current cannot flow through the diode this way here. So it's as if the diode is not there in normal operation. The only reason the diode is there is because the transistor is being used as a switch. Whenever you stop current in any circuit, there is an inductive kickback. And I don't want to go into this in too much depth at this moment in time. And basically what will happen is if current is flowing, if you have this IGBT switched on and then you switch it off, there is going to be an inductive kickback, which is going to make this terminal here more positive than this terminal here. And those inductive kicks can actually get very high in voltage. And IGBTs are very, very sensitive devices to both high voltage and high current. So what this diode does is that it allows that current to go this way. Excuse me, it allows the current to flow this way and dissipate to another part of the circuit and not damage the IGBT. Okay, so you will see as we go on that all of the IGBTs that we use do have this diode inside of it. So what's the circuit equivalent, the mechanical equivalent? Now, I have to put out a safety announcement here. I know it sounds stupid, but we're in 2020, and I have to caveat everything I say with, do not put your hands on electricity. I know this picture has got a hand and it's going to push a button, but do not touch electricity in real life. It's a shame that I have to say that, but that's where we are these days. So we've got the collector of the transistor here, we've got the emitter of the transistor here, and we've got the gate here, and I've drawn it as a spring-loaded switch. And basically, with an IGBT, all you do is send a signal to the gate. In other words, press with your finger on this button, this way here, and it makes a circuit. The collector and the emitter become connected together. And then if you remove your finger from the circuit, then the switch opens, and the collector and the emitter are not connected anymore. That is how we use IGBTs in a UPS at AMETEK SCI in our pulse width modulated UPS systems. And I'm going to go on to show you how we do that a little bit later on. But that is the very, very basic principle of an IGBT. And as you can see, the difference between an IGBT and an SCR is, yes, you send a gate signal to an IGBT, it switches on. You remove the gate signal from the IGBT, and it does switch off. And we'll show you that in the circuit in just a moment. And for those who just want a little bit more of a robust, similar to the check valve situation, we've got these solenoid controlled valves. And basically what you have is the collector here, That's the input, and the emitter is the output. And we have our gate drive here. And the gate drive is a plunger with a seal. So as you can see, this seal here is not allowing the fluid in the collector to get through to the emitter. The gate drive signal is off. And in the solenoid control valve, what we have is we have a coil. And if we send a signal to the coil, in other words, we send a signal to the gate, then what's going to happen is this is going to become magnetized. It's going to pull the plunger up. And you can see now there's a path for the fluid to flow from the collector to the emitter. And once again, if we remove the gate signal, we return to this position here. The plunger closes and it is now open. So it is like a switch. It's either open or it's closed, depending on whether it has a gate drive. Okay. So now we've put it in exactly the same circuit we've been using all the way through this presentation. We've got the DC source on the left, we've got our lamp on the right, and now we've got a gate drive going to our IGBT. Same principle as the SCR. We push button S1 and that will send the gate drive to the IGBT. So with the gate drive removed, it is an open. It's an open switch. Current cannot flow with the gate drive removed. Okay? In either direction. There's a caveat to that because of the diode, but I'm not going to go into that during this presentation. It's too complicated. But in theory, in simple theory, an IGBT is an open circuit when you don't send a gate drive to it. Okay? And then if we do send a gate drive to it, so you can see switch 1 has been pressed, allowing the gate drive to get to the IGBT here, current will flow and the lamp will light. Okay? But as I said, different to the SCR, if we then remove the gate drive signal, switch 1 is now open, gate drive has been removed, it goes back to an open again, and the lamp is off. So you have complete control on an IGBT. You can switch it on and you can switch it off. You switch it on by giving it a gate drive and you switch it off by removing the gate drive. And here's what the IGBTs inside an AMETEK solid state controls UPS look like. On the left here, the white one, you can see we've got one transistor here and one transistor here. And the terminals, that says 1, which is this terminal here. This one says 2, which is this terminal here. And this one says 3, which is this terminal here. Okay. And you can't see it very well because this is shipped from the manufacturer like this. It has a copper collar. And actually, if you look at this right-hand picture here, you can see the gate signals here, and you have to have, it's a gate emitter signal that you send, so you have to connect to the gate and the emitter. You can see that there are 2 pins standing up here. On the left hand picture, there's actually a copper collar sent from the manufacturer, and basically that's there to short together the gate emitter terminals, so static electricity during shipment cannot damage the device. Once again, I've said that IGBTs are very, very sensitive to high voltage and high current situations. They're not very robust when it comes to those, so they have to be protected. Okay, and remember, I said there's a diode. You can see that there's actually a diode here inside these IGBTs. You can't see it very well on the right-hand side, but there is a diode connected across the IGBT here. Full transparency. Okay, so that's the basics of what the devices are, how they work. So now we're going to show you how each device is used. So this picture here is a half-wave rectifier. On the left-hand side, you have a sinusoidal waveform, an AC waveform. Let's say it's 120 volts coming from your outlet, okay? Now, in most half-wave rectifiers, that will then go through a transformer. This one here gives us isolation. We're not going to go into that today. That's a different topic of conversation. But let's say this transformer is just a one-to-one transformer. So we have 120 volts going in here. We have 120 volts coming out of the transformer here, okay? Well, we have our diode here, and it's only going to allow the positive portions of this sine wave through, because that is the only point where the anode is more positive than the cathode. So if we put an oscilloscope across this resistor here, and sorry, this is a European drawing. In Europe, we draw our resistors like this, as opposed to the zigzag style that we draw in the US. But this is a resistor, and if we put an oscilloscope across that, this is the waveform that's going to come out. And you can see that the negative going portion of the sine wave here is completely missing, okay? We have now made DC. The question is this DC? Yes, it is. This is pulsating DC. Current is only going in this direction, okay? Here, current goes in this direction here, and then for the negative portion, current goes in that direction, and then we go back to that direction. That is what makes AC, alternating current, is going in two different directions. For DC, the current is only going in one direction, direct current, okay? Now here's a full wave rectifier. In the previous slide, let me go back to it. We're wasting this whole half wave. That whole half wave is not being utilized. It's extremely inefficient. And you've also got to remember that half wave is still going to be energizing the coil for this transformer. So there's still going to be energy used during this process, but we're not utilizing it on the output. So it's a very wasteful way to do things. So some clever guy one day, I'm sure it was in his garage or something like that, invented the full wave rectifier. Somebody much more clever than I am, and figured out a way to take the AC waveform on the left here, put it through a full wave bridge rectifier, and get and utilize both halves of the sine wave. And I'm going to go into how they do that in just a moment. And just for clarification, depending on how you were taught at school, in engineering or wherever, this bridge rectifier is identical to this bridge rectifier. They are just drawn slightly different. Most people, when they went to university, were probably taught this bridge rectifier circuit first. But this top one here is the one that most UPS manufacturers use to draw a bridge rectifier. And this one here is a single phase bridge rectifier, okay? So let's show you the power flow for the bridge rectifier. So remember, on an AC waveform, for one half of the wave, this side of the AC source is going to be more positive with respect to this side of the AC source. That's only for the positive portion of the waveform. Now remember that current will only flow from anode to cathode in a diode. So if you follow the red lines and the arrows here, current will flow up through that first red diode, anode to cathode, and then it gets to this point here. And there is a blue diode here, and that blue diode has the cathode at the top. So it's going to block current. It will not allow current to flow down there. It's like an open circuit. So current continues to flow this way, down through the load, and back through this diode here. Remember, anode here, cathode here, so current is allowed to flow through. And remember, the whole point is to get from this point here in the power supply, and we have to return to this point here to complete the circuit. So we can't use this diode because that takes us back to our starting point. So it has to be this diode here and this diode here that conducts. And that will give us this output waveform here. Okay? It's for the positive half of the sine wave. And here's the really, really clever thing. Whoever designed this bridge rectifier, the genius that he is, I should do some research and find out who he is. Now, when we have the negative going portion of the sine wave, I say negative going just for ease. When the current's going in the other direction, this side of the power supply is now more positive with respect to this side. So current is getting driven out this way. Okay. Now, current goes to this point here. Now remember, this point here is more positive than this point here. So we don't, this diode here, it doesn't conduct. It doesn't go through that diode. It goes through here, up through this blue diode here. And look what's really interesting. That now flips our waveform to a positive going waveform. If you look at the load here. So this is now positive here. And if we go down through the load resistor, we can't go this way because that's taking us back down there to where we started. That's not what we want to do. We have to get back to this side of the power supply. So we go down here. Anode here is more positive than the cathode. So it does go through there and it gets back there. So the amazing thing is we have flipped this portion of the waveform. On this side here, it is below the zero line on our oscilloscope. And now we have flipped it above the 0 volt line. So once again, here, current was flowing in that direction for the positive portion of the sine wave, and in that direction for the negative, that direction for the positive, that direction for the negative. Now we're going this way, this way, this way, and this way. It's going in one direction, direct current, and we are utilizing both portions of the sine wave, much more efficient than the half wave rectifier. Okay. But it has its downfalls, just a normal bridge rectifier. Because if you think about it, in UPS systems, the reason we have a rectifier is for a charger to charge our batteries. Okay, and our batteries have to be charged at a certain voltage to keep them healthy. So in most situations, we use lead acid batteries here in the US, and the float voltage for a lead acid battery is 2.25 volts per cell. Please check your battery manufacturer's datasheet to make sure. It could be 2.23, 2.27, but for most cases, you can say it's 2.25. And in the majority of cases for industrial UPSs, we have a 60-cell battery. 60 cells times 2.25 volts is 135 volts. And those batteries really need to be charged as close to 135 volts as possible. So when we make DC, we have to make that DC stay at 135 volts no matter what. And you say, well, that should be easy. Just make the input to the rectifier bridge equivalent to whatever the output is to make it 135 volts. Well, that's not going to work because we rely on the grid power from whichever plant our UPS is connected in to supply power to the rectifier. So here's an easy example for you. Let's say we use the 120 volts out of the outlets that are in your home or office, okay? Now the peak voltage for that waveform is 170 volts for a 120 volt outlet, okay? The peak voltage is 170 volts. Now, there is an equation that gives you the average voltage from a full wave rectifier. The equation is 2 volts peak divided by pi, and that equals, for a 120 volt system, 108 volts DC. So the average of this waveform here is 108 volts DC. Okay. So most people will say, well, let's increase the 170 volts so that this equation here equals 135 volts. Well, yeah, that would work, but it would only work when our input is 120 volts. And we don't know what your input's going to be. It could be 115, it could be 125, it could be anywhere. So on our next page, let's say it was 100 volts. Let's say it was maybe a substation far away from the main connection and volt drops in the cable, whatever reason. The 120 volts in this situation was 100 volts. Well, that makes the peak of the sine wave now 142 volts. And if we use our equation, we've now gone to 90.4 volts DC. So the DC changes with changes in the AC. So that means if we just use diodes, then we couldn't control the voltage going to our batteries. And therefore, we're not going to be able to regulate the voltage going to the batteries, and they will be undercharged or overcharged, which is not a good situation. Undercharged causes sulfation of the plates, which eventually leads to crystals forming, and that will basically eventually lead to short circuits in the plates and will kill your battery. And if you overcharge them, especially lead acid batteries, then the electrolyte will dry out, and you could cause your batteries to go into thermal runaway. So you have to be very careful about the voltage that you charge your batteries. So the only way you can do that is to use SCRs in your rectifier bridge. Okay, so in this circumstance here, we've now replaced the two top diodes with two SCRs. And what that allows us to do, it allows us to switch the power that's going through, and that allows us to regulate the power. So let's start with this first portion of the sine wave here. We're actually switching the SCR on at that point there in the sine wave. So we've switched the SCR on there. Now remember, it's very important. Once you switch an SCR on, remember I told you when you remove the gate signal, it will not switch off. So it remains on for the whole portion of the sine wave until this point here. And then when I do in my classroom, live classroom, I said, well, what's that point there to everybody? And everybody shouts out, it's the zero crossing point. Okay. And the zero crossing point means there is no potential across the anode and the cathode. That means current stops flowing through the SCR. And what happens when current stops flowing through an SCR? It switches itself off. Okay, so that's the important thing to remember about an SCR. We can switch it on in a rectifier, but we have to wait until the zero crossing point for it to switch itself off. So we can only control when it switches on. So for the bottom half of the sine wave here, we're switching it on around about there. And obviously design of the bridge rectifier flips it up above the 0 volt line, and that's it switching on there. For the next portion, we're leaving it till really late in the phase cycle, and we're switching it on there, which is this point here. And we're only allowing a very small portion of the sine wave to get through. And then on this last one, we're switching it on really early in the sine wave, and we're allowing a large portion of the sine wave through. In truth, we could switch it on right at this zero crossing point here, and that would allow this whole portion of the sine wave. It would be like that if we really wanted to. But basically, it gives us phase regulation. We can switch it on and off. We can switch it on whenever we want. The zero crossing line switches it off. Okay. So going back to our circuit, if we had this waveform going in here, okay, and the only time we send a gate drive to this SCR is at this point here, we send a gate drive at this point here, our resultant waveform will be this. This portion doesn't get through, this portion doesn't get through, and this portion doesn't get through. It's only when we send a signal to the SCR that it gets through. I hope that's clear. So the SCR can regulate the output for a changing input. So we're going to go back to our example. For a low input voltage, this was the 100 volts AC waveform going in with a peak of 142 volts. We are switching on the SCRs just at the peak here. So basically the average would be our, it's a slightly different equation, but our average would be that level there. And then if our voltage went back to 120 volts, our peaks went up to 170 volts, we're switching the SCRs on this side. And we're regulating the output. The level of the average of this output here is the same as the previous one. And then if the input voltage goes high and the peaks go to 190 volts, we switch the SCRs on really late in the cycle, and our average still remains the same. So basically, where we switch the SCRs on determines the average output of the rectifier circuit. And that's how we can regulate the charger inside a UPS. Okay. So now we're going to move on to the IGBT and how it's used inside a UPS. So the SCRs are used inside the rectifier circuit. The IGBTs are used inside the inverter. And sorry if I didn't clarify this. A rectifier converts AC to DC, and an inverter converts DC to AC. Okay. So what we're doing here in this example is when we don't send a gate drive to the signal, to the IGBT, sorry, this is the resulting output waveform. Nothing comes out here. As you can see, I've actually replaced the lamp with a transformer. It's still a load, and you'll see in a little while why I changed it to a transformer. But if you put a oscilloscope across there with no gate drive signal, you are not going to get an output. Okay? And then if we momentarily send a gate drive to the IGBT for this length of time, we start the gate drive there and we end the gate drive there, we actually create a pulse on this transformer. Okay? And the peak voltage is whatever the DC source is. And in a UPS, that is going to be your battery, which is being charged at 135 volts DC if it's a 60 cell system. Excuse me. Okay. And then what we can do using electronics, we can decide when to switch these IGBTs on and off. And we do that using pulse width modulation, PWM. Now, a very simplified picture here. If you have very small, thin pulses, you have a low average voltage. And if you have wide pulses, you have a high average voltage. So with PWM, what you can do is using a steady DC source. Remember, the DC inside your UPS is going to be 135 volts for a 60 cell system. We can actually adjust the output voltage with increasing and decreasing the pulse width. And what we can also do is we can shape the output waveform to look like more like a sine wave. So here is the an IGBT H bridge inside a UPS. So basically here is your input. This would be your DC bus inside the UPS, your 135 volts DC for a 60 cell system. Okay. And we have one IGBT there, one IGBT there, one IGBT there, and one IGBT there. And then that goes through an inductor here and a transformer here, and then out to the load circuits. And you'll see in the next slide, For the positive part of the waveform, what we do is we use pair A transistors and we switch them both on at the same time. Okay, and that allows a path. If you follow this, it allows a path along here down through this IGBT, and it makes this side of the transformer here. I'm going to just draw it with my arrows. That makes that positive with respect to this point here. So when IGBT pairs A are on, the output waveform is positive with respect to the 0 volt line. And what we can do is we can switch them on, and we do it pulse width modulation. What we do is we start with thin pulses, then we make them thicker, and then we make them thinner again. And the mathematical average of that is a sine wave. We do use some capacitors and inductors to clean it up and make it an actual sine wave. But the average, the mathematical calculation of that pulse width modulated waveform is kind of like a sine wave. Okay, so for the positive half of the sine wave, we switch IGBTs on and off to create that pulse width modulation. And then for the negative portion of the waveform, we switch IGBTs B, the pair, on and off. And once again, some clever person came up with this H-bridge configuration, and power flows along here. And now this side of the transformer is more positive than this side. And that gives us our negative side of the sine wave. And remember, when you don't send a signal to an IGBT, it is an open. So no current can flow through these IGBTs if they don't have a gate drive signal. Okay. And then the diagram below shows the output of the H-bridge. Looks like at the primary of the transformer, and then the dotted line is what it looks like on the secondary side of the transformer when we've put some capacitors in there to filter it. It turns it into a beautiful sine wave. Okay, now remember, this voltage here is going to be 135 volts DC for a 60 cell system. This voltage here is going to be 135 volts DC for a 60 cell system. Okay, now remember, if you lose power, that voltage, the batteries are going to start supplying the inverter bridge, and the voltage is going to go down. So as that voltage goes down, the advantage of PWM is we can widen all of these pulses and make the average higher, and we can maintain the output of this system at 120 volts exactly using the pulse width modulation. Okay, so I think that is our last slide. So now is your opportunity to ask any questions. I will do my best to answer them, and I'm very humble, so if I do not know the answer, I will tell you I do not know the answer, and I will try and find out for you, and I will send you an email with the answer. Now remember, it's going to take 30 seconds for you to type in a question for me to see it, so I'm going to have to put in some dead space here to allow the questions to come in as necessary, and that's pretty much the hour up, but I'm going to go for probably another 15 minutes to answer anybody's questions. Okay, so Carl's just asked, can we get a copy of the slides? At this moment in time, we do not give copies of the slides, but the webinar is recorded. Okay, so you can go, and as long as you've registered for this webinar, you can watch this webinar at any time. I think it sends you a link after the webinar is complete for you to do that. Okay. And while I wait for any more questions, don't forget that AMETEK Solidstate controls, all of our field service engineers are working hard throughout the whole country and internationally, following all the COVID-19 guidelines. So they are out there working. So if you need anything, then you can give us a call. And we will be restarting our training classes here in Stafford and at our California office in the near future. So look out in your emails for when we will be starting our training again. Okay, so how do you test an SCR to see if it is good or not? The very, very simple test for an SCR, and with most semiconductors, there's some caveats to it, is with no power connected to it, you get a fluke multimeter, you put it on resistance, and you go from anode to cathode and from cathode to anode. It should be an open circuit in both directions, okay? Near enough all SCRs fail short circuit, okay? So if it's an open or it's high resistance, it is good. If it is a short, it is bad. That is the most rudimentary test you can do to test an SCR. What I would always recommend is you lift all cables going to the SCR to test it, because there may be other paths that give you a funny reading. So always try and disconnect the anode and the cathode from the circuit the SCR is in, or at least one side of it to test it. Okay. What are the advantages of using IGBTs in your rectifier instead of SCRs? Very good question, Peter. I'm not the best person to ask for that. We do make it's basically power factor correction rectifiers is what it's called. Using IGBTs in the rectifier allows you to lessen the harmonics taken and increase the power factor to nearly unity in a rectifier circuit, which helps with efficiency and helps with reflected harmonics on your system. So that is the advantage of using IGBTs in the rectifier. In truth, in industrial UPSs, it's very rare that we use IGBTs in the rectifier, and it's not really called for. The SCR rectifier is far more robust than an IGBT rectifier. IGBTs are very, very susceptible to failure, and SCRs are not. They are just so robust. So that's why we use SCRs for reliability. But the advantage of IGBTs is you increase the power factor correction, the power factor into the UPS rectifier enormously by using IGBTs. I think for our rectifier, it's somewhere around about 80 to 85% efficiency. And there are some IGBT rectifiers that can get up to high 90s. But that's why they are used. How do you deal with the harmonics generated by the square? Good question, Jose. We don't, in our PWM UPSs, we don't create a square wave. We create that synthesized sine wave. And the way that we deal with the harmonics is using harmonic chokes and capacitors. We tune the filter circuit to make it a sine wave and get rid of the harmonics that we don't need. In our older style, well, actually, we still make the DSE now. In our ferroresonance systems, we do use a square wave in the inverter, and it just needs more capacitors. And the inherent nature of the ferroresonant transformer deals with the harmonics generated by the square wave. A PWM has much less harmonics than a square wave generated ferroresonance system. Okay. Let's have a look if there's any more questions. Why do rectifiers always come with a blocking diode while battery chargers don't? Hesham, good question. I don't know if that's actually true. What you will find is in parallel rectifiers, they usually have a blocking diode. If you can, basically, if you connect two chargers in parallel, you would have a blocking diode in each charger. And what that prevents is if one charger rectifier bridge fails, then that blocking diode will stop the battery and the other healthy rectifier from feeding current into that failure. So that's why we have blocking diodes in chargers. So I don't think there is a difference between a rectifier and a charger and blocking diodes. It's only when they are in parallel that you will have a blocking diode. Some people call it a best battery selector as well. To me, that's nonsense. I'm not going to go down that route. The diode is there just to block current going back the way into a failed rectifier bridge. Hopefully that answered that question. Jose asks, what is the expected lifetime for the IGBTs compared to SCRs? Ooh, that's a good question. Engineering might have to get back on that. I know that the meantime failure rate on SCRs is probably much higher than IGBTs. The technology has been around for way longer. They are just so robust. It is extremely difficult to break an SCR. Believe me, I have tried it many times in the lab here in Houston, and I've had to put a huge amount of current through an SCR to fail it. IGBTs, on the other hand, are very easy to destruct. So I would expect that the SCRs are the meantime failure rate is much higher than an IGBT. But I'm going to take a note of that question, and I'm going to see if engineering can give you more information on that, Jose. Is the output of the inverter 120 volts from the 0 point to the peak, or is it 120 volts between the positive and negative peaks? Okay, that's a good question. The output of the inverter is 120 volts RMS. So it's actually 170 volts peak to the zero crossing line, and actually 340 volts peak to peak for a 120 volts inverter. I hope that answers that question. So the reason and the way that we get that is the transformer winding will be designed in such a way so for whatever the output of the inverter bridge is, the secondary will have turns to make the output the required voltage, which in your circumstance for the question would be 120 volts RMS. Okay, looks like we don't have many more questions coming in. I'll hang around for another 3 minutes and see if any more questions come in. Once again, our training classes will start again soon. Our labs in Houston and in California are, in my opinion, state of the art. They are absolutely fantastic. We have several systems that we have bugs put in. We try and do as much practical work as we can. And there is a lot of practical work. We put faults in the systems. We teach you how to find these faults, what to look for. The classroom portion is also very, very good. In Houston, we have a smart screen where we can do a lot of stuff, draw waveforms on the screen, a lot of good stuff. And also, just giving it a plug, on Thursday nights when you come to our training, we treat you to either a big steak night, depending on the weather, or we take you to a local restaurant and wine and dine you as well for having to put up with us speaking so much. So if you want any details on the training, please go to our website, AMETEK Solidstate Controls, and then click on the training tab, and that will give you more information on how to arrange training with us. We do training on our PWM systems, our DPP UPS, and we also do training on our microfarad system, our SE and our DSE systems. Okay, it seems like we don't have any more questions. I'm going to wait until the clock turns to 11:10. And if there's no more questions, I thank you very much for taking time out of your Wednesday. We really do appreciate it. I hope the information was good and you learned a little today. You will be sent a survey. In that survey, it asks I think you asked what topics you would like to see at our next webinar next month, and we really want to hear what you have to say. I'll design a webinar for whatever you want, so please let us know what you want us to talk about, and we'll design a webinar for that, because I could talk for hours on stuff that you don't want to hear. So let me know and I'll see what I can do. So that's 10 past 11 Central Time. Thank you very much, everybody, for your time. It was a pleasure having you. Once again, you will get a link for the recording of this webinar. Hope you enjoyed it. And until next time, please do take care.